Okay, so we have seen center of mass of continuous systems. By integration, and the standard examples that we've developed from that center of mass of a thin semi-ring, then thin semi-disk, then solid cone, then hollow hemispherical shell, and finally solid hemisphere. Okay, these are the examples that are standard, and you should memorize the formula for them. Okay. So let us move to an application example of utilizing the above kind of formula. So now if we have this situation, we have sort of a thick ring like this, sort of a thin ring. Have a ring which has a significant inner and outer radius difference, because, and then what we've done is we've sliced this ring into half. So this is our and this is the bisecting axis. So y-axis is again the bisector or the symmetry axis. Origin is the common center of curvature of the inner and outer boundary. Okay, so let's say this is A and this is B. So given that A is equal to 6 millimeters and B is equal to say 9 millimeters, you have to find the position of the center of mass. Let's start with this. Okay, so let's understand how we can tackle this question. So one is, of course, we can do integration, slice it into semi rings, but the difference is the limits for the radius will be integrate. The limits of the radius will be from E to B instead of 0 to R. So that's one option. So we slice this into semi rings like this. So this semi ring is of mass Tm. So sigma will be m upon okay. And area that will be this mass. Now this thin semi ring's own center of mass will be here at a y coordinate of 2r by pi. Okay, that is the direct result that we used from earlier. So therefore, the y coordinate of the center of mass is okay. Limits A to B.
So B minus A can be factored out, right?
Yes, you can do also that also. Okay, so I can either you can factorize and simplify further, or you can just substitute the values, whatever be the case. So you'll get the numerical value of the position of the center of mass. Okay, so hope the application of integration and the standard method used over here is both are clear to you. Okay, now we move on to the next section of application of the concepts of center of mass, which is going to be collisions, where we will look at essentially conservation of momentum for a system of bodies as they collide. Okay. Typically, we will start with the collision of two particles or two bodies, okay, with each other. So as a system, their linear momentum will be conserved because when they collide, there are only mutual impact forces or collision forces. The external force on the system is zero. So let's start with that. So we will develop some standard formulae and methods for solving collisions. But first of all, we will define collisions and then classify the different types of collisions that occur. Okay. So collisions is a very significant portion of this chapter and applications of the concepts we've learned earlier. So any situation where a moving body or particle makes an impact on a moving or stationary and exchanges momentum as a result of impact force called a collision. But generally, we will start with the collision of two bodies. You can take a situation like this. So this is suppose a smooth surface. So what happens here is that after some time, suppose the second block is at rest. Okay. Just arbitrarily in this example, I'm considering that this block is at rest. So what we'll see is that after some time, this one comes and hits this. As they come in contact, this will experience a force like this, and this will experience an equal and opposite force on this. This is the impact force on the block M2 by M1, and the impact force on M1 by M2. Now, understand that as vectors, these are equal and opposite. Because they are an action-reaction pair. So as a result of this, typically what may happen is, especially because it looks like M1 is a lighter object, or definitely its size is less, so we may expect that it's a lighter object. So what we may expect is that after the impact, this block goes off with a velocity like this, and this block might even recoil, that is, it might come back with a velocity like this. So this is an example of what is called a head-on. I'll explain the term head-on. It is also one-dimensional. So I'll explain the classification of collisions into head-on versus oblique also, but you can see this is an example of a collision. And above is the definition of collisions. Okay, just make a note of this first. Then we'll look at more examples and definitions. So any situation where a moving object collides with another object which is either moving or at rest, or makes an impact, such that as a result of the impact, there is some exchange of momentum between the two. That kind of situation is called a collision. And in the more extended definition of collision, we can also have a situation where more than two objects collide simultaneously. Another kind of situation you can observe for a collision could be, for example, something like this. Now, suppose this body is moving in this sort of direction, and this is moving in this sort of direction.
Sir, the screen has stopped sharing.
Okay, just a moment. Okay, so it should be back online now, right?
Yes, sir.
Okay. Now suppose this is what is happening. Two bodies are moving like this, such that after a while they come in contact like this. While they come in contact now, the collision forces that will act, because they are like spherical bodies or discs or whatever, the collision impact forces will be along the center to center line. So this is going to be the force acting on one because of two, and this is going to be the force acting on two because of one. And as a result of force, the momentum transfer here will happen in such a way that the direction of motion will change. Okay. So the first one had a momentum in this direction and it experienced an impulse, let's say in some direction like this. So as a result of that, okay, it's okay. So its final velocity, let's say, becomes something like this. Second one was moving like this and it experienced an impulse downward. So its final velocity, let's say something like this. So this is an example of what we call an oblique collision. So the difference between this second example called the oblique collision and the first one called the head-on or one-dimensional collision is, in the first one, all the vector quantities are one-dimensional vectors. They are along the same axis. Whether we look at the velocity vectors before and after impact, or we look at the impact forces, they're all one-dimensional along a common axis. So it's an example of head-on or one-dimensional collision. Whereas in the second example, if you look at the initial velocity and final velocities, they're not along one common axis. They're in a 2D plane, and the impact forces are also in the same 2D plane. Okay, so that is why the final velocities and the initial velocities, they are not collinear vectors. They are not along the same axis. Hence, it is called an oblique collision. Okay. Or you can also call it a two-dimensional collision example. But the technical name given to this kind of collision is oblique collision. So first of all, on the basis of these two, we will classify collisions as head-on versus oblique. And we will start with the analysis of head-on collisions. Okay. However, one important thing is that whether you're dealing with head-on collision, like in this situation, is if you consider the colliding objects as a system, you can see for that system, the external force is zero during the collision. It is only action-reaction internal pair of force. Similarly here, even in the oblique collision case, you can see for the system consisting of both the colliding objects, the external force is zero. So basically, whether we are dealing with head-on or oblique collisions, okay, whether we are dealing with collisions of two bodies or collision of more than two bodies simultaneously, for our system, the linear momentum will be conserved, because during the collision event, it is only the mutual action-reaction pair force which is acting. There is no external force acting on the system. So that becomes the first aspect about collisions to understand, that by definition in a collision, what is happening is that there is impact between two bodies or more, such that they transfer momentum among themselves, or they redistribute the momentum through the action-reaction pairs of forces or impulses. There is no external force. So in any collision or any type of collision, for the system considered as the colliding objects or bodies, the linear momentum is conserved. Because the net external force on the system during that impact is going to be zero. Okay, so oblique or head-on, whichever type of collision we are dealing with, linear momentum is conserved for the system. Let's make a note of this point.
The oblique collisions, can you again explain like the examples of it?
Yes. So
Sir,
yes.
sir, any other examples of oblique collision?
Can we?
Any other example of oblique collision?
Actually, see, any situation where two bodies are colliding such that their final velocities and initial velocities are in different directions, that is called an oblique collision. Okay. So it could be two spheres like this. It could be, for example, a particle. Suppose it is moving in this sort of direction
Okay, sir.
and
So
it
like,
collides with, let's say, another body, which is, so as it goes like this, okay. Suppose in its path, there is an object like this, okay. And this is like the top view, suppose, on a smooth horizontal plane. So when they come in contact, what is happening is that the collision force will act like a normal reaction force. No? So it will be in this sort of direction.
yes, sir.
Okay. So the particle was initially going in a direction like this, velocity, and it experienced an impulse like this. Okay. So it will sort of, after impact, it will go off, let's say, in this sort of direction. And the body will go off in this sort of direction.
So it's not necessary that it will change the velocity of both the objects, right?
It will have to, no? Because impulse is acting, no? Force integrated over time. A certain amount of force is acting for a certain duration of time while they're in contact. So the momentum of both will change, no?
Yes, sir.
What my point? Yeah, I mean,
Yes.
practically speaking, suppose the second object is very, very heavy compared to the first one. So there's a very small change in its momentum. Okay, but there will be some change nonetheless. Okay, it might be negligible if the masses are very different. Like the first one is very light and the second one is very heavy. Okay, so then it can be a negligible change, but nonetheless there has to be some change. You understood the point?
Yes, sir.
Okay. So now let us look at both type of collisions, head-on and oblique, in more detail. So we'll start with head-on collisions. Or they are also called one-dimensional collisions. So you can define head-on collisions in such a way that the final and initial velocities or momenta vectors of colliding objects are along the same axis. That is called a head-on collision. So if these are the initial velocities, let's say in general, we are considering a situation where both colliding particles or bodies are initially in motion, but they are moving along a common one-dimensional axis, such that when they come in contact, the contact force or impulse, whatever I consider, that is also along that same axis. And as a result of that, after impact, what I see that the final velocities are also along that same axis. Now here, for example, V1 can become negative. This can also happen, that this one recoils. Okay. But even if it recoils, it's collinear as a vector. It's along the same axis. So if the initial and final velocities or momenta are along a common 1D axis, that is, all are collinear vectors. So if they are collinear vectors, then the collision is called a head-on or a one-dimensional. Now further, head-on collisions. We will divide into categories called perfectly elastic, inelastic, and perfectly inelastic.
Sir,
Hmm.
sir, how can we mathematically show that in a collision momentum is a quantity that's being conserved?
Yeah, so that is from the above situation. You can see that when momentum for a system of particles is conserved, when the net external force acting on it is zero. Remember the impulse momentum theorem?
Yes, sir.
Okay, so basically for any system of particles, we have the theorem that net external force is equal to rate of change of momentum of the system. Okay. That is rate of change of total mass into velocity of center of mass, where m is basically summation mi, okay, that kind of thing. So this now follows that if the net external force is zero, then the rate of change of momentum is zero. That means, what about the momentum of the system? It is conserved. You understood the point?
Yes, sir. Got it.
Okay, now when two bodies are colliding, as a result of the impact, there is only an action reaction internal force pair acting. Now, there's no external agent who's applying any force.
Yes, sir. Got it.
Yes, I'm scrolling now. So basically any collision situation, in fact, whether it is head-on or oblique, involves conservation of linear momentum. But apart from that, there is also one more consideration which determines what happens as a result of the collision, how much momentum transfer there is from one body to another. And that is the whether it is what we call perfectly elastic collision or inelastic collision or perfectly inelastic. So by definition, perfectly elastic is a situation where total kinetic energy of the system is conserved. And this will primarily happen in that situation where the bodies colliding are made of highly elastic material. Like imagine tennis balls colliding with each other, or soft rubber balls, etc., or blocks made of rubber. Whereas if you consider objects made of inelastic materials like two wooden blocks, or uh, soft plastic materials which are not that elastic and rather are very easy to compress, etc., so those kind of materials, when they collide, there will be some loss of kinetic energy. There is some loss, or what we can also call dissipation, of kinetic energy on impact. And the third, and this category, it's a very specific case where colliding objects stick together. Now, this also involves a loss in kinetic energy. So that is why the name is inelastic for the ones where there is loss of kinetic energy, and perfectly elastic where there is zero loss of kinetic energy. But inelastic also we are breaking into two categories: a general inelastic situation where there is just loss of kinetic energy, whereas a perfectly inelastic case where there is loss of kinetic energy, but in addition, the objects which are colliding are also sticking to each other. So they're going to move as one common object. For example, if a bullet strikes an object and gets embedded inside it, so now the bullet and the object move together. Okay. Or two objects are made of sticky material, so as they come in contact, they stick to each other and then move as one common object. Those are examples of perfectly inelastic collisions. Okay, so now let us look at an example of a perfectly elastic head-on collision and how we can solve.
Sir, can you just hold on for a minute?
Okay. This part, the classification.
Yes, just a graph. I mean, fine.
Okay, done.
Yes, sir. Yes, sir.
Okay. Now let's look at an example. So we have that situation we had drawn earlier, and we have a smooth surface with one block moving directly towards a second block, but the second block is initially at rest. So this is the block A, this is the block B. This is moving with a velocity V0 and this is at rest initially. This is a smooth surface. So given masses of A and B are 2 kg and 3 kg respectively, and V0 is 12 centimeters per second. Now A makes a head-on collision with B. Find their final velocities after impact. If the collision is perfectly elastic. And second, if it is an inelastic collision with %20 loss in kinetic energy on impact. Okay, so now what we will do is we will observe the momentum conservation principle. Okay, apply it to this given situation, and depending on whether we are dealing with the first part where there is perfectly elastic collision, that means there is conservation of kinetic energy. So the system's initial and final kinetic energy should also be equal. Or the second case where there's a 20% loss, that means the final kinetic energy should be 80% of the initial kinetic energy for the system. So we will use these two principles, the energy relation along with momentum conservation relation, to find the two unknown quantities, which are the final velocities of A and B. Okay. So just try the first part because it's even easier with the conservation of kinetic energy. We'll discuss. So write the equations for momentum conservation and conservation of kinetic energy and try to figure out what the final velocities will be. Okay. Okay, so let's solve the perfectly elastic case first. Okay. So before impact, we have this situation. Whereas after impact, let us assume that this is the situation. So first of all, there is conservation of linear momentum. For the system. So masses of the block are 2 kg and 3 kg. So 2V0 plus this one is 0 will become 2VA plus 3VB. So 2VA plus 3VB is equal to 24 kg centimeter per second. This is our first equation. and there's also conservation of kinetic energy for the system because it is a perfectly elastic collision. So V0 square plus 0 is equal to VA square plus 3 by 2 VB square. So we have VA square plus 3 by 2 VB square is equal to 12 square. This is our second equation. Now this combination of equations has to be solved to find out VA and VB. So what we can observe is that equation 1 can be written as 2 times V0 minus VA is equal to 3 times VB. And equation 2 can similarly be written as V0 square minus VA square is equal to 3 by 2 VB square. Just rearrange the terms a bit like this. Now what we can do is we can divide equation 2 by equation 1. So we will see that we'll get V0 plus VA by 2 is equal to VB by 2. So we'll get so this is like an additional equation we are getting. Now if you compare equation 1 and 3, it's easy to solve for. Now notice that we are getting VA with a negative sign. So the negative sign actually what it means is that after impact E will be traveling in the opposite direction. So this basically means that after impact E will be traveling in this direction at 2.4 centimeters per second and B will be traveling in this direction at 9.6 centimeters per second. That is the significance of the negative sign that we are getting for VA. Okay, so make a note of this and yes.
I didn't get how you got the third equation. Shouldn't it be 2VA plus 3VB equal 2VA plus
Equation,
sorry, second equation. Second equation. V2.
this one, the kinetic energy one. You see, it is half MA V0 square plus 0 is equal to half MA VA square plus half mb vb square. Okay. Now just substitute ma as 2 and mb as 3. Na? So you'll get this.
Okay, so we don't have to take the combined mass of the system then.
Why will take the combined mass beta? Kinetic energy to मतलब system में दो blocks हैं which are having individual velocities ना. So
Okay.
kinetic energy is a scalar quantity. So the total kinetic energy of the system will be that. We got it now?
Achha, okay. Got it.
Okay. So first of all, note this down and understand this part completely. Okay. Then second part, what we have to do is instead of conservation of kinetic energy, which we have written, second part, it is an inelastic collision. Okay. With 20% loss of kinetic energy. So that means your second equation will get modified. Okay. So this basically means that the final kinetic energy will be 80% of the initial kinetic energy. Instead of equating the final kinetic energy with the initial, which we have done in equation 2 for the first part, okay, we will equate the final kinetic energy as 80% of the initial or 0.8 times the initial. That will mean that our equations are getting a bit modified. Finish writing this down, then we'll discuss that part. Okay, so let's look at the equations for the second part now. So we have our momentum conservation.
So will not.
You calculated, beta?
No, sir.
Okay. Okay, so this equation remains the same. Okay, but now we have that the final kinetic energy should be 0.8 times the initial kinetic energy. So okay, so this will become like this, that VA square plus 3 by 2 VB square will become 0.8 times V naught square. So these two equations have to be solved. This. Okay. So we have Yeah, so let's see the solution of these equations. So in
Two
this
answers can
case,
come.
sorry,
Can two answers come? Like,
because actually
sorry.
this will be, now you have to solve a quadratic equation, you know. So there'll be two
Yes, sir.
answers, but we will reject one answer out of the two, because what will happen is, from the diagram you can understand that VA cannot have a value which is greater than V naught. No, it has to have a value which is less, or it has to have a negative value, whichever be the case. Okay, you understanding?
Yes, sir.
So on the basis of that, we will reject one of the roots. So anyway, so the first equation is now like this, that 2VA plus 3VB is equal to 24 in centimeters per second. So from here we can write VB as how much? VB will become 8 minus 2 by 3 VA. And we will substitute this in the first equation, in the second equation. So we have VA square plus 3 by 2 VB, which is 8 minus 2 by 3 VA whole square, is equal to 0.8 into 12 square. So we will have 1 plus 4 by 9 into 3 by 2. This is the coefficient of VA square. Okay. Then minus of, this will become 3 by 2 into 32 by 3 VA. And then plus of 3 by 2 into 64. It's going to be 0.8 times 144. So then solving this quadratic equation will give us the value of VA. So become 1 plus 2 by 3, isn't it? So 5 by 3 BA square, okay, minus 16 BA. And then this term will become 32 into 3, so that is 96 minus 144 into 0.8.
115.2.
Just a second. Okay. Yeah, so this is becoming how much? 115.2, no?
Yes.
So now we have here minus 23.2 is equal to 0. So we will get the value of VA from here. So we should write it as 16 plus minus. Okay, but we will reject the plus root because of the reason I told you. Okay. It become plus 4 into 5 by 3 into 23.2. So the route that we will take will be the one with the minus sign. So VA will become minus of 1.28 centimeters per second. Whereas the other route, if we had taken the plus sign, would have been 10.87, which is a route that we will reject because A being a lighter particle compared to B, it is more likely that it will recoil. Also, if we take that second route, then we'll probably get VB as a negative quantity, which does not make sense. Okay, VB has to be a positive quantity. So we have this value that's 8 minus 2 by 3 VA. So when we take this value of VA, we get VB as whereas if we take this value of VA, that 10.87 root, then we'll see that we get a negative value of VB, which is not logically possible. Okay, so this is an example of a elastic head-on collision. Okay. So people, with this we end today's session. Next time we will look at, sorry, this is an example of an inelastic collision, and we also saw perfectly elastic. Okay. Now next time we will see how we can develop exact formulae for these different types of collisions using these concepts. And we'll also discuss another collision parameter called coefficient of restitution. So in the meantime, you can finish all questions from HC Verma up to about question number 38, okay, which involves applications of conservation of linear momentum as well as center of mass. That's it for today's session, people. Wish you all the best and have a nice day.
Thank you, sir.
Thank you.